So this has a chair structure. And they're showing this. The reaction is OH minus and DMSO. And the question says, draw the major E2 reaction product formed when cis-1-chloro-2-ethyl cyclohexane, shown below, reacts with hydroxide ion DMSO. So one person might have thought, literally the directions tell you it's an E2. Right, so you might have thought this could have been an SN2, right? Weren't careful, right? If we just look at this, right, what kind of alkyl halide do we have? Primary, secondary, tertiary alkyl halide. Secondary. Got to get better at that. Just find the number of all you got to do is, there's one hydrogen, it's secondary. If there's no hydrogens, it's tertiary. If there's two, it's primary. So it's secondary. So it still could be it could be anything, right? E1, E2, SN1, SN2. So what's the next thing we look at? We look at the reactivity of the nucleophile, or the base. Does it have a charge, basically we're asking. Does it have a charge? Yes, so it's reactive. So that eliminates E1 and SN1. Now we look at the size. And usually this is a pretty small one. So we might be worried about SN2 here, but the instructions literally say, right? So make sure you read instructions. Instructions say, draw the E2. They tell you this is an E2 reaction. Good. So know it's an E2. So we know it's E2 because instructions told us that, or we could have eliminated it and got there, but we have a chair. And what did I tell you all about chairs and leaving groups? What position do they have to be in? They have to be axial. Right now, this chloride is equatorial, so you need to be able to do a ring flip. Got to be able to do a ring flip still. All right, so if I number these carbons, if I pull down on carbon 1, pull up there, everything else rotates around. Now, if E2, we got in the right conformation, just like you rotate to make things anti-periplanar. Got in the right conformation. Now you look for beta hydrogens from the carbon 2, in this case, the carbon with the chlorine on it, with the leaving group on it. Beta hydrogens, and the hydrogens have to be what position? Also. Have to also be axial and on the opposite face. So if this chlorine is axial and up, you're looking for beta hydrogens that are 1, 2 bonds away, 1, 2 bonds away, that are also axial but down. So it's either this hydrogen or this hydrogen. So if I label them A or B, which one is the most likely one here? A or B? B. Zaitsev's product, right? Zaitsev's rule. This is only a secondary alkyl halide. This is not a very big base. If I take B, it'll lead to a more substituted alkene. E2 mechanism. Double bond there. No wedges and hatches ever with pi bonds. You've never seen me draw a wedge and a hatch with a pi bond. Don't do it. So there's a product that also could look like this. Same thing. 1, 2, 3, 4, 5, 6. Yeah, just to reiterate, it has to be anti-periplanar, right? See how they're 180 degrees apart? So that one's axial up, one's axial down. All right, so taking a look at another sapling type question. It says, draw the main organic products of the reaction. Indicate the stereochemistry, including all hydrogen atoms at each stereocenter. Omit byproducts such as salts or methanol. Okay, so for this one, again, first thing we identify is what type of alkyl halide do we have. So you can write, we'll do E1, E2, SN1, SN2. What type of alkyl halide do we have? Primary, secondary, tertiary, allylic, benzylic, lone pairs. What kind do we have? Secondary. Does that eliminate any possibilities? No. Darn it. Okay, so then we look at the nucleophile. Is it reactive? Yes. Remember, this is really this. All right, that nucleophile is pretty reactive. It has a negative charge. Does that eliminate anything? Limits E1 and SN1. Right, the ones with carbocations. If we have a negative charge species, we're not going to make a carbocation. So down to E2 and SN2. If we have a negative charge thing, we're never going to do SN1 or E1. Right? So now we're down to E2 and SN2. And honestly, it's going to be both. And they want both. Right? So they want both products. So let's do both. Which one do you want to do first? E1 or you want to do E2 or SN2 first? Let's do E2 first because it's there. Right? So we'll really have to redraw this twice. So let's do we'll do the E2 one first. So E2 is coming out first. So doing E2, we need to find the leaving group, right? So let's number these carbons. 1, 2, 3, 4, 5, 6. We want to find the beta hydrogens. All right, so we numbered our carbons, which you all should do. So we're looking for beta hydrogens for E2. So beta from carbon 2. How many different types of beta hydrogens are there? 2. There's one on carbon. Which carbons have beta hydrogens? 1 and 3, right? And which one are we going to take? 1 or 3? Got to be careful. We got to make sure. We want to make the Zaitsev product, but we got to make sure that they're anti-periplanar to each other. They have to be on opposite sides. I still like this one. This is still the best one to take. Why? Well, it leads to the most substituted alkene, the Zaitsev product. And the H and the bromine, this is wedged, that's hatched. That means they're anti-periplanar to each other. They're opposite sides of the ring, right? They got to be on opposite sides of the ring, otherwise they won't react. If they're not opposite, it won't work. E2 reaction. What's our product going to look like? Get a new pi bond between which two carbons? 1 and 2. So that there. 1, 2, 3, 4, 5, 6. E2 product. Zaitsev product. Most substituted product. So now to do the second part of this, we needed to do the SN2 reaction. All right, so the SN2 reaction, so we needed to do the find the reaction with sigma star, which is on the opposite side. So the bromine is wedged here. Sigma star would be hatched to be the opposite side there. So again, one-step reaction. Nucleophile comes to the back side, pushes that out. What's going to happen to that stereo center? So nothing happens to this one. Nothing changed there. And what was hatched now becomes wedged, and the nucleophile has gone to the back side. That's the SN2. So you've inverted this stereo center when we talked about 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, so again, how do we identify stereo centers? Has to be sp3 hybridized and bonded to 4 different things. This is carbon 2 and carbon 1 are actually bonded to 2 different things, or all bonded to 4 different things, so they're both stereo centers, 1 and 2. So what did you make here? If I showed, if this was A and this is B, what are they to each other? What kind of relationship do they have to each other? They're diastereomers. All right, they're diastereomers. How do I know they're diastereomers? This asymmetric center on carbon 1 stayed the same. I don't even know if it's RS. I know it didn't change, right? And I know carbon's 2 stereo center, asymmetric center did change. So these two, A and B to each other, they're diastereomers. They have the different physical properties, right? Have at least one asymmetric center that's different, one that's the same. All right, look at another one. Again, first question we ask ourselves. So let's just E2, E1, SN1, SN2. What kind of alkyl halide do we have? Primary, secondary, tertiary? Secondary. So that doesn't eliminate anybody. What kind of nucleophile do we have? Reactive or less reactive? Is it reactive, right? Again, I added that in there, so it's reactive, so that eliminates E1 and SN1. So we're down to E2 and SN2. Then we look at how the size of the nucleophile. Is this a big or small nucleophile? Big, right? Make sure you can recognize what this means as far as what a structure would look like. So it means this is that tert butyl group. That's a big, bulky base. It's reactive. Good. So we're probably thinking E2 then, right? Large base, not going to do SN2. Now, again, once you have E2, you got to find your beta hydrogens. So how many types of beta hydrogens are there? How many types of beta hydrogens? Just one. Just one. Carbon 1, 2. There are no hydrogens on carbon 3. So there's only one type of beta hydrogen. It's this one. Carbon 1. All right? The one on 2 is attached. That's attached to the. That's not 2 bonds away.
Okay.
It's 1, 2 from the carbon, not from the thing. Never. That's the classic thing. I think I said that right at the first day. People are going to try to do eliminations on the carbon of the leaving group. Don't do it. Don't do it. This never gets eliminated. No, 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 no. Beta hydrogens. 1, 2 from the carbon. All right. So that's our leaving group. That's only one type of alkene we're going to make. But now we need to make sure it's anti-periplanar. And right now, if you looked at this, they're not anti-periplanar. Right. So we need to draw the Newman projection. That's what I would do. And if I was looking here, at my head would be a hydrogen. My right would be the ethyl. At my feet would be a phenyl. Right, it's an H. So an H there, and a bromine here. This was carbon 1 in the front, carbon 2 in the back. Gotta be able to draw those Newman projections, just like the chairs. Still gotta be able to do that stuff. So now you need to rotate one of the carbons, 1 or 2, doesn't matter which one you rotate. You just need to rotate one of them because you need to get this bromine on this carbon, on carbon 2, and this H on carbon 1, 180 degrees apart. So let's rotate carbon 1. And we're going to need to rotate 120 degrees, right? 120. We take this H and put it over here. So we're going to rotate clockwise 120 degrees. So I didn't move carbon 2 at all. So the bromine stays there. Of course, still needed the staggered conformation. There's the H. There's the ethyl. It's right there. Carbon 1, carbon 2. So now our bromine and our hydrogen are anti-periplanar. So now we can draw the mechanism here. Taking the H, electrons can go there. Take that out. So you can look and see, right? The methyl and the H are on the same side, and the ethyl and the benzene ring are on the same side. So when you draw your alkene, carbon 1 fits over here, carbon 2. There's your methyl. There's your ethyl, and there would be your H, and there would be your phenyl ring. So the biggest thing, I think, just to make sure you do all the steps you need to do. You need to decide it's E2. You need to draw the correct you need to identify the beta hydrogens. See how many types you have. Right? This one you only had one type, so it's pretty easy. Right? Draw the Newman projection of what it currently is. Rotate however you need to get the leaving group and the hydrogen, the beta hydrogen you want, 120 degrees apart. And then just identify where things are at on the new alkene. So this is one of the sampling ones. I think this is around number 10. Let's do our process. They're asking for the SN1, SN2, U1, U2. What type of alkyl halide do we have here? Primary, secondary, tertiary. Secondary. Is our base or nucleophile reactive? Yes. So that eliminates SN1 and E1. Is it bulky? Yes, that probably eliminates SN2. So we're looking for beta hydrogens. So circle this carbon. So we're going single bonds, 2 bonds away from that. So I see 1, and then I also see 3 more out here. So 2 different types. Now this is one of those ones where sampling is going to want the non-Zaitsev. They want the Hoffman product here. But I mean, like remember if you remember, I wrote in the class notes, it was tertiary usually is a for sure thing in a really bulky base, but sometimes secondary will get you there too. And they really want they really want that one here. I would take both answers on a test if I had it written this way, just because it's not that clear. But the answer they want, so for all these ones, if these are all B, they want you to take B. Right. So it doesn't even have to be anti-periplanar at this point because there's 3 hydrogens there, so you don't have to worry about it. Although it was lined up pretty nice for you here if you did have to do that. So the product they want, the answer they want, is just this. All right, notice how this center right here doesn't change at all. Nothing happened to it. It's there for the ride. So the other way you could do it, if we did the other E2, so this is what sampling wants, but another thing I could have asked you for, just show me, make sure you can do that. If I redrew it and did if we did the Zaitsev product, so say we could do the Zaitsev product, if we go for this H. So this is another way to do it. All right. Now the alkene. Now again, you don't have to do the Newman projection here because they were already anti-periplanar in the plane. So the 2 methyls are on the same side, and the H and the ethyl are on the opposite sides. You could do the Newman projection though, and you'd see that they already are in the right conformation. But you get that product. This would be the Zaitsev product, and this would be the Hoffman product. So I could ask you, I could say, draw me 2 mechanisms. Show me the Hoffman product and the Zaitsev product. Could you do that? Right. What I would, again, don't put 2 sets of arrows on the same molecule. Just redraw the molecule again. Yep.
Would the Hoffman product be the minor product
A
then?
lot of conditions dependent. I wouldn't ask you to know that. Remember, I wasn't going to really push too much on the major minor. I mean, you should know like Zaitsev's rule. If I said, right, which one's a major product, if it's just about Zaitsev, then you should know the most substituted one's the most stable, most likely product. So then on the very next sapling question, I think it's 11, that one was 10. They say, now what's the major E2 dehydrohalogenation reaction, E2 reaction? Draw the major organic product here. Now they're really saying, okay, look, it's an E2. Your base, right? That's a reactive base. Plus and a minus. Now they're saying, okay, that's small. Right, which one's it going to go for? Is it going to go for these H's out here? Yeah, it could. But the likelihood is still now it's going to follow Zaitsev's rule. Right? It's going to go for the more substituted, to make the more substituted product that's already lined up anti-periplanar for us. So you get the same product. For the very next one, they show that example of if you change the base size, what you can get. So I just made one up. I'm telling you it's an E2 reaction. This is a secondary alkyl halide. So the first thing you know, if it's an E2, I'm telling you it's an E2 or even an E1, the first thing you should look for are beta hydrogens. So take a second and see if you can find the beta hydrogens, the number of the types possible here, and which one makes the most sense to eliminate. So identifying the beta hydrogens, if I number my carbons here, so 1, 2, 3, and carbon 2 is the carbon with the leaving group on it. So I'm looking for hydrogens 2 bonds away from that. So the hydrogens off carbon 1, and the 1 hydrogen off carbon 3. Now, if I label these HA and these HB, which one is more likely to be taken, do you think? What's going to lead to the more stable product? Which letter is that? A or B? B. So we'd say B if we were thinking Zaitsev. That would lead to the more substituted alkene, right? But it's actually going to be A. Resonance. Think about resonance. Right? Resonance is even better than Zaitsev's rule. So we do that E2. Right? Remember that? You see that benzene ring there? It's not that many. Think about stability, right? Resonance. You know about resonance. Things can be conjugated. You know it's always a good thing. Right? You even could have drawn both things out. Right? Sometimes it's helpful to just draw out both possible products and just take a look at them. Say, okay, which one's better than why? Right? Write that on a test. Be like, well, here this one has resonance, this one has Zaitsev. I don't remember which one's which. That's okay. I'd rather have you see that. I'd rather see that and show me that you knew that there was one of them was more important. Right? Write down what you know on the test.
Wait, so if you did choose B, there wouldn't be a pi there?
There would be a pi bond.
Oh,
so if I chose B,
yeah.
It'd be the pi bond would be a tri-substituted pi bond, which would be good according to Zaitsev's rule, but now it's a little more complicated because now we're also thinking about resonance. So this is a di-substituted pi bond, but it also does resonance, which makes it even more stable. Resonance, remember, is a key. So also just to note, this is also a trans di-substituted alkene. Again, trans alkenes are also more stable than the cis ones. Things want to be away from each other. Or the E versus the Z. E is more stable than Z. So what if I took that same exact secondary alkyl halide, and under different conditions, I'm going to tell you it's going to be an E1 reaction. What's the product going to be for an E1 reaction? More specifically, what's the mechanism going to be for an E1 reaction? So let's remember those same 3 carbons. Let's see if we can draw the mechanism for an E1 reaction. So E1 mechanism, what's the first step going to be? Leaving group leaves. And we're going to form a carbocation. When we form a carbocation, what do we need to be thinking about? Rearrangements. Rearrangements. All right. So in this case, we have a secondary carbocation. We start with the secondary. Can we make this more stable? How can we make this more stable? Which way do you want to go? Carbon 1 or carbon... So we're looking for things 2 sigma bonds away, right? Methyls or hydrogens are out... Like sigma bonds 2 bonds away from the carbocation, right? So on carbon 3 we have H's. Carbon 1 we have H's. Carbon 3 we also have methyls. Right? What do we want to do? What do we want to move? Which one? Which one? If you move carbon 3, you make a tertiary carbocation, which would be good, but not as good as making a benzylic secondary carbocation. Right? Again, resonance. Right? We have a choice here. I could move this hydrogen and make a tertiary carbocation, which would be good, but that's not as good as a secondary benzylic, right? Resonance wins. Resonance wins. Right? What are the ways to stabilize a carbocation? Hyperconjugation, pi bond resonance, and lone pair resonance. And lone pair resonance is better than hyperconjugation, right? Tertiary carbocations only have hyperconjugation. So we did that H shift from carbon 1. What do we have? So H shift. Leaving group leaves. So now we have the plus charge is now on carbon 1. And somebody might say, wait a second, that's a secondary carbocation. You went from secondary to secondary. No, I didn't. I went from secondary to secondary and benzylic. Right? Secondary and benzylic. So it's a much more stable carbocation. Am I done rearranging? Can I make it any more stable? So when you're done doing all your rearrangements, then you re-look for beta hydrogens with E1. Right? You got to do all your rearrangements first, and then you look for beta hydrogens again. So now where are the beta hydrogens at? On carbon 2. There are not any, that's the only beta hydrogens that are available. So now we're going back, right? So it's weird because it's like that hydrogen we just put over there might get taken away. But so now the solvent comes in, right? The unreactive, no negative charges, right? SN1 and E1 don't like negative charges. Plus charges are okay. Do that E1 reaction. What's the product going to be? So here's E1. We're actually going to get the exact same thing we got for an E2 reaction. 1, 2, 3. The conjugated pi bond. Different mechanism though. Right, yeah, so what happened to that? There's also the byproduct to balance our charge, of course. We end up with a protonated solvent. The solvent has the hydrogen. So there's also this in the solution. And there's also, right, of course, Br minus is still floating around too. Right, balance your charge. Br minus, the initial leaving group on the left is still there as well. But usually they'll just ask you for the organic product. But E1, SN1, they don't like negative charges. All right, so this one doesn't have any negative charges, so it's not reactive. Make the carbocation, check for rearrangements. Try to find the most stable thing you can for rearrangements. Remember, allylic and benzylic's even more stable, right? More resonance, the better, right? Lone pairs is even better yet. You're trying to make more stable carbocations. And then you're also trying to make things that have resonance, if you can, which is more important than Zaitsev's rule. So up in number 22 in sapling, and this question is asking, consider the following pair of reactions, predict the type of elimination mechanism, so we already know it's either E1 or E2, and predict which reaction of the pair will create at a faster rate, and draw the correct organic product. All right, so let's decide if it's E1 or E2. So what type of alkyl halide do you have in the first one? Primary, secondary, tertiary? Tertiary. And the next one you have a secondary, right? Has an H. Right? So that's still good for E1 or E2. That works. OH minus, is that a reactive or unreactive thing? Reactive is negative charge. So we're thinking E2 all the way for both of these. E2 all the way. All right. So E2, so that means we want to find the beta hydrogens, right? So how many types of beta hydrogens do we have? So if this is carbon 1 in both cases, we're going single bonds, 2 bonds away from carbon 1, and it's carbon 2. How many types of beta hydrogens are in the first one? So if we call this one A, this one's B. How many types of beta hydrogens are there? 2. There's hydrogens out here. Right? I could ask questions that easy. Draw the beta hydrogens. Tell me what type of alkyl halide this is. Right? Make sure you can do those simple things. Right? So there's 2 types. I'm not really worried about these though out here. Because they're not going to lead to a very substituted product. This is not a very bulky, big nucleophile or base. So I'm always thinking Zaitsev normally, right? So I'm thinking of this one, and they're already anti-periplanar, so that's awesome. So what's the mechanism going to look like? Take the H, electrons go there, carbon-chlorine bond breaks. All right, we're going to get a new pi bond. And it's going to have simply methyls on each side. They're all methyls. The 2 wedges are methyls. 2 hatches are also methyls. And that would be carbon 2 and 1. So tetrasubstituted alkene, really stable by Zaitsev's rule, right? Really stable. Yep.
But if it is a tertiary,
Mm-hmm.
how is that?
E2 can have tertiary. Oh yeah, absolutely. E2 likes tertiary. That goes fast. That goes really fast. That goes really fast because look at the product we made. We made a really stable product. So E2, look at your notes. It's all good. Tertiary is all good. E2 is the one that's weird. E2 will take everything. Right? Yep. SN2 will not take tertiary. That's right. Well, this one, again, be careful. This is not a beta hydrogen. This is the classic mistake people make. Hydrogen's bonded to the carbon of the leaving group. This is not a beta hydrogen. Do not try to do that elimination. I guarantee you, I will see somebody show me arrows going from here and kicking that out. Somebody's going to try to eliminate this. And they'll make a pipe. They'll put these electrons going there and kick this out. Don't do it. This hydrogen, it can do pi bond. Now in this case, there's an H over here and the two methyls, 2 and 1. Now the question is, we both know these are E2 reactions, so they're both E2. Which one's going to be faster? Or are they going to be the same rate, or is one going to be slower? Top one will be what? Faster. Because you're forming a more substituted alkene. Zaitsev rule. It's going to take less energy to make that because you're making something more stable. Go back and look at your class notes. It's in there.
Can this also be E1?
It can't be E1 because we have a reactive nucleophile. It's only E2.
Okay. So why didn't you use the
Slower.
hydrogen from the carbon one, off of carbon one?
Because those are not beta hydrogens. Right? Don't forget the stereochemistry needed for an E2 reaction. Right? Right? You needed things lined up, 2 bonds away.
Carbon one, it needs to be, the hydrogens need to be off of carbon two.
Yes.
Okay.
Right? When I say single bonds 2 bonds away, I'm referring to the carbon that has the leaving group on it. Right? 1, 2.
Okay.
1,
so
2.
The carbon with the leaving group is usually going to be carbon number 1. And you're going
That's how I draw it, yeah. The single bonds, the hydrogens for these eliminations need to be 2 bonds away from that carbon.